Welcome to a journey into the depths of the cosmos, where reality bends and particles dance. In today's exploration, we delve into the fascinating realm of quantum field theory, a framework that unveils the very fabric of space itself. Buckle up because we're about to venture into the awe-inspiring world of quantum mysteries and theoretical wonders. To comprehend quantum field theory, envision the universe as a vast stage, and fields as actors donning different roles. These fields pervade every nook and cranny, even what appears to be empty space. They're the underlying forces that create and shape particles, influencing their interactions and behaviors. Quantum field theory transcends common intuition. Imagine particles constantly appearing and disappearing, and the very notion of empty space being a bustling sea of activity. This is the essence of the quantum world, a place where the impossible becomes the norm. Quantum field theory has profound implications for our understanding of the fundamental nature of the universe and its smallest constituents. Let's explore a few of them. Number 1. Particle behavior and interactions. Quantum field theory provides a consistent framework for describing the behavior and interactions of particles, including how they exchange energy and momentum through various force-carrying particles. It allows us to understand the underlying rules governing the behavior of particles at the subatomic level. Number 2. Particle creation and annihilation. Quantum field theory reveals that particles can spontaneously come into existence and disappear in a vacuum due to fluctuations in the quantum fields. These are called virtual particles, and they contribute to various physical effects, such as the Casimir effect and the Lamb shift. Number 3. Quantization of energy. Quantum field theory introduces the idea of quantization, where energy levels are quantized into discrete values rather than being continuous. This concept underlies phenomena such as quantized energy levels in atoms and the discreteness of particle properties. Number 4. Spontaneous symmetry breaking reveals that symmetries in the mathematical equations describing particle interactions can be spontaneously broken in certain conditions. This concept has implications for understanding the origins of particle masses and the behavior of fundamental forces. Number 5. Quantum entanglement. Quantum field theory is closely linked to the phenomenon of quantum entanglement, where particles can become correlated in ways that defy classical intuition. This non-local connection has implications for quantum information theory and the potential for future quantum technologies. Sources: established theories. Many brilliant minds have paved the way for our understanding of quantum field theory, including Alain Aspect, John F. Clauser, and Anton Zeilinger, who won the Nobel Prize in Physics in 2022 for their work on quantum entanglement. Another luminary is Murray Gell-Mann, who introduced the concept of quarks, the fundamental building blocks of matter. Exploration: Quarks Crash Course. Quarks are never found in isolation due to a phenomenon called confinement. Imagine you have a bunch of colorful building blocks that make up the protons and neutrons in an atom. These building blocks are called quarks. Now here's the interesting part. Quarks don't like to be alone. They're social and always hang out with other quarks. But the catch is, they're a bit shy. So when you try to separate them and pull them away from each other, something strange happens. Instead of just getting farther apart like regular things would, the energy between them increases. It's like stretching a rubber band. The more you pull, the tighter it gets. This energy keeps growing and growing as you try to pull quarks apart. And before you know it, you've got so much energy that it's like creating new quarks out of thin air. So instead of letting you see individual quarks, the universe creates more quarks and they join up with the original ones, forming new particles called hadrons. In a way, it's like quarks have this special bond that only gets stronger the more you try to separate them. This is what we mean by quark confinement. Quarks are never found alone. They're always held together by this incredible force. Speculative element: multiverse theory. Now let's enter the realm of speculation, the multiverse theory. Picture a cosmic tapestry, where our universe is just one thread in an infinite fabric of universes. While this idea isn't universally accepted, it's a thought-provoking notion derived from quantum field theory and string theory. String theory, originally proposed by a group of physicists in the late 1960s and early 1970s, is a framework aspiring to unite the forces of the universe, including gravity, and reconcile quantum mechanics with general relativity. It suggests that at the tiniest scales, particles are not points, but rather tiny strings vibrating at different frequencies. Though still theoretical, string theory offers exciting potential to bridge our understanding of the quantum and macroscopic worlds. Significance. Practical applications. While quantum field theory delves into the deepest realms of theoretical physics, it also yields tangible applications. It underpins the Standard Model, our current understanding of particle physics. It helps us decipher the interactions of particles and predict phenomena like the Higgs boson, which was discovered at CERN in 2012. The Large Hadron Collider at CERN has been instrumental in pushing the boundaries of quantum field theory. Works by Lisa Randall and Nima Arkani-Hamed continue to shape our understanding of particle physics and its connections to the fabric of space-time. Unveiling the cosmos. As we conclude our voyage through the intricacies of quantum field theory, remember that space isn't just an empty canvas. It's woven from these quantum fields, shaping everything we see and experience. Reflective from Feynman to multiverse speculation, from the quirky to the profound, quantum field theory grants us a glimpse into the marvelous workings of the universe. Thank you for joining us on this exploration. As we leave the quantum realm, let's carry its mysteries with us, inspiring curiosity and awe in our pursuit of understanding the cosmos. This has been a journey through the tapestry of space, guided by the threads of quantum field theory. Until our next cosmic adventure, keep questioning, keep learning, and keep your sense of wonder alive.